Hello everyone, my name is Yifan Qiao, and I'm currently a fourth-year PhD student at UCLA. Today, I'm going to present our paper Canvas, Isolated and Adaptive Swapping for Multi-Applications on Remote Memory. This is a joint work of my collaborators from UCLA, UCSD, Tsinghua, and Princeton University. Data centers today face memory challenges. On one hand, with the end of Moore's law, the growing of memory capacity is getting slower and hitting the memory capacity wall. On the other hand, memory is often underutilized in data centers, resulting in a great resource waste. One promising direction to solve the problem is to use remote memory and unstrand idle memory on servers over a network. In a remote memory system, the host server is connected to a remote memory pool via fast network, such as RDMA or CXL. Application can transparently access remote memory, leveraging the OS kernel paging and swap system. Once application accesses data in remote memory, it triggers a page fault, and the kernel swap will fetch the page for application. While the concept of remote memory sounds promising, it requires concrete effort for real deployment. Various prior work have targeted improving, for example, the efficiency and reliability for remote memory. However, most of them focus on optimizations for a single application, while ignoring the multi-tenant nature of today's cloud. In multi-tenant cloud, applications on the same server often share remote memory to maximize their overall throughput. However, interference can occur in this shared setting, causing existing systems lose their efficiency. Here, we ran a motivation experiment with 4 real-world cloud applications on the current state-of-the-art remote memory swap system. To serve as a normalized baseline, we first run each of the 4 applications individually, with 25% of their working set cached in local memory, as shown as a straight line here. Well, when we run all 4 applications together, we notice that they actually experienced an unpredictable slowdown. Despite we have already used Linux C group to partition and isolate each application's CPU and local memory usage, applications still experienced severe throughput drop and huge performance variation, and this will lead into vast quality of service violations. Such high overhead actually is a result of severe interference that stems from the shared kernel remote database. Conventional isolation technologies such as Intel CAT and Linux C group can only partition and isolate local resources such as CPU cache lines, CPU cores, and local memory, but none of them touch the remote memory database in kernel. Actually, we identify 3 interferences in different layers of the shared database, as elaborated below. The first category of interference arises from the shared swap resources. For instance, the kernel maintains a swap cache for recently swapped and prefetched pages. The swap cache is protected by log primitives to serve as a centralized component to prevent risk contagion. However, Haoran applications therefore must compete for the log for each of their swap operations. This similar contention also happens for the swap partition, and in our case, it's the remote memory. Allocating and free remote memory during swap can also cause heavy log contention and eventually decreases the overall swap throughput by 56%. The second interference occurs in the shared swap prefetcher. The OS kernel leverages a pattern-based prefetcher to detect sequential access patterns of an application and prefetch it for it. However, when the prefetcher is shared, access traces from Haoran applications are mixed, causing the prefetcher to fail in identifying any pattern from them. We observe that the prefetch contribution drops significantly for Haoran applications comparing to running them individually. Third, the kernel swap is originally designed for disks, and it does not control the network bandwidth usage for swap. As a result, RDMA bandwidth competition may occur among applications or between the application and the kernel prefetcher for their demand and prefetching requests. Therefore, the network contention can further increase the 99th percentile latency of the network by 2.1 times. Driven by these observations, Canvas builds a fully isolated swap data path. By letting each application control its own dedicated prefetcher, swap cache, swap partition, and RDMA bandwidth, Canvas eliminates all previously mentioned interferences. More interestingly, isolation also further unlocks the opportunities to customize the swap system by adapting them to different application behaviors. Note that this is not possible with current Linux kernel because Linux kernel only makes conservative and general assumptions over application, and it does not differentiate different behaviors of co-running applications. But with swap isolation in Canvas, Canvas can segregate each application's unique behaviors and adaptively optimize the swap system for them. Here, I will compare Snappy and Spark and show how Canvas optimizes them differently. Snappy is a single-threaded application with a sequential access pattern. Therefore, the kernel prefetcher works well for it after the isolation. However, Spark, on the other hand, is a multi-thread application based on Java. It includes user mutator threads as well as other garbage collection threads and other threads in JVM. Among all the threads, only the mutator threads have sequential access patterns, whereas others do not have any pattern and do not need to prefetch. Therefore, Canvas enhances the kernel prefetcher with a per-thread pattern tracker to identify patterns only for the mutator threads and prefetch eagerly for them. Consequently, the prefetcher in Spark has a higher bandwidth usage than Snappy due to more prefetching requests, so that the kernel prefetcher can compete RDMA bandwidth with the application's demand. Therefore, Canvas employs a two-dimensional RDMA scheduler to coordinate bandwidth for the Spark application threads and its prefetcher. Finally, as Spark swaps more intensively, it also experiences heavier log contention in its swap partition. Canvas therefore designs an adaptive allocator to reduce the remote memory allocation rate and hence reduce the log contention. Next, I will introduce the design of our adaptive remote memory allocator in details, and you can find more details of other two adaptive optimizations in our paper. Before diving into details, let's first briefly revisit how current Linux kernel manages remote memory. We know that the kernel manages local physical memory by partitioning it into an array of pages, each typically in 4 kilobyte size. Similarly, for remote memory, Linux also partitions the space into an array of swap entries, where the size of each swap entry is also 4 kilobytes to host a swapped out page. When swapping out a page, the kernel has to make space on the remote memory by scanning the swap entry list to find and allocate an available entry. As this list is shared by the whole system, kernel swap has to lock the whole list to synchronize concurrent swap outs. Likewise, when swapping in a page, kernel will fetch it from some swap entry, and after reading the page, kernel will free the entry to release remote memory. Again, entry free is also protected by the same lock. As we can see, the kernel manages remote memory in a relatively simple manner, and actually it works well for simple applications such as Snappy, which does not frequently swap. However, for swap-intensive applications such as Spark, this design is no longer efficient, as it involves too many repetitive entry allocation and free for swap operations and causing heavy log contention. Now, let's go back to Canvas and see how its adaptive entry allocator solves this problem. since Canvas has an isolated swap partition for each application, now it can trade off space for efficiency by reserve and swap entry for each swapped out pages. To be specific, Canvas attaches a small field to each page and memorizes the ID of the allocated entry at the first time to avoid repetitive allocation. I will show a concrete example. During swapping, Canvas will memorize the entry ID and swap a reserved entry as a one-to-one mapping for the swapped page. Therefore, subsequent swap outs can follow this mapping to write the data directly to the reserved entry without lock. Even under the swap intensive setting, as most pages can have the reserved mapping, they can perform lock-free swapping. Hence, the lock overhead is greatly reduced. Finally, the reservation can put remote memory under pressure. So Canvas inversely trade off time for space under remote memory pressure by filling reserved mappings adaptively and their swap entries following the kernel LRU list. Now it's come to our evaluation. We implemented Canvas on top of Linux 5.5 and evaluated it with 6 cloud applications and a total of 11 workload combinations. With the next few slides, I will demonstrate how Canvas improves the throughput as well as reduces the performance variation of co-running applications. Other detailed results can be found in our paper. We first co-run Snappy, memcached, and XGBoost with different Java applications under varying local memory ratios. As shown here, Canvas outperforms FastSwap by an overall of 3.5 times and 1.9 times under 25% and 50% local memory ratio, respectively. This is actually a joint contribution of Canvas isolation and adaptive optimizations. Canvas also greatly reduces performance variation for co-running applications. Here, we fix the setting of Snappy, memcached, and XGBoost, and we co-run 3 of them with another different Java applications under 11 different workload combinations. As Snappy, memcached, and XGBoost have the same workload across all the experiments, we measure their performance variations under 25% of local memory ratio. As shown in this figure, Canvas reduces the performance variation for each of the 3 applications by an order of magnitude, which with an average of 7.4 times variation reduction. In conclusion, Canvas is an isolated swap data path for shared remote memory, and it's equipped with adaptive optimizations. Through Canvas, we aim to convey 3 main messages. First, due to the multi-tenant nature of cloud, performance isolation is necessary for real deployment on remote memory. Second, Canvas is the first system that improves performance and quality of service for remote memory. Third, isolation enables adaptive optimizations for further performance boosts after reducing the performance variation. Our code is open sourced on GitHub. Thank you, and I'm happy to take questions.